All right, let's talk about something that's running behind the scenes of pretty much every big app you use. Data replication. Basically, it's the whole game of keeping the same data in a bunch of different places. And trust me, it's way, way trickier than you'd think. I love this quote from Douglas Adams because it just hits the nail on the head, right? When you're dealing with data, putting all your eggs in one basket, relying on just one single computer is basically begging for disaster. Because we all know things do go wrong. Hard drives crash, networks get flaky, and that's exactly why we need copies. Okay, so you might be thinking, if making copies is so complicated, why even bother? What's the upside? Well, let's get into it, because it really boils down to three massive wins that basically make the modern internet possible. So first up, it's all about speed. We're talking about reducing latency, which is just a fancy word for delay. Think about it. If you're in Europe, you don't want to wait for data to travel all the way from California, right? Having a copy nearby makes everything feel snappy. Second, we get availability. This is a big one. It means if one server just decides to, keel over, the whole app doesn't crash and burn with it. Another copy just steps in and takes over. Seamless. And third, there's throughput. With a bunch of copies, we can spread out all the user requests. This lets us handle a huge amount of traffic without any one computer getting totally swamped. Okay, so how do we actually do this? Well, the most popular way by far is something called leader-based replication. You might also hear it called master-slave. It's really straightforward, which is why you see it in tons of databases you've probably heard of, like PostgreSQL and MongoDB. It's kind of like a little three-step process. So one copy of the data gets to be the leader. All changes, we call those writes, have to go through the leader. No exceptions. The leader then takes those changes and broadcasts them out to all the other copies, which we call followers. Now, when someone just wants to read data, they can ask the leader or any of the followers. The real genius here is that by forcing all the changes through one central point, you get this really clean, simple order of events. It keeps things from getting messy. And this diagram shows it perfectly. So a user wants to update their profile picture, that's a write operation. You see that request goes straight to the leader. The leader does its thing, updates its own data, and then pushes that change down these replication streams to the followers. Now, anyone else who wants to see that new picture can ask either of the followers for it. See? Super clear. One path in for changes and multiple paths out for reading. But here's where it gets interesting. There's a really critical decision to make. How does the leader talk to the followers? One way is synchronously. Think of it like sending a registered letter. The leader sends the update and then waits and waits until at least one follower sends back a message saying, "Yep, I got it." Only then does it tell the user their change is safe. It's safe, but it can be slow. The other way is asynchronously. This is like sending a regular letter. The leader just sends the update out and hopes for the best, moving on immediately. The big takeaway? It's a classic trade-off. Synchronous is safer but slower. Asynchronous is way faster, but it opens the door to a whole new set of problems. And that brings us to the biggest headache with the asynchronous approach. It's a little thing called replication lag. All it means is the time delay between when something changes on the leader and when that change actually shows up on a follower. So what actually happens when the followers fall behind? I mean, what does that feel like for you, the user? Normally, this lag is tiny, just a fraction of a second. But when things get busy or the network is having a bad day, that lag can blow up to several seconds or even minutes. And that's when things get weird. This whole situation leads to a concept called eventual consistency. It sounds kind of nice, right? It's basically a promise that, if you stop making changes and just wait, all the followers will eventually catch up to the leader. But that word, eventually, it's doing a lot of heavy lifting. It's not a guarantee of when, and that's where the really bizarre user experiences come from. And I guarantee you have felt this before. You post a comment on social media, or you update your profile, and you immediately reload the page, and poof, it's gone. Your old picture is back. And for that split second, your heart sinks because you think the whole thing just failed. Yeah, that incredibly frustrating moment has a name. It's called the read your writes problem. And this diagram shows exactly what's happening. Your update, the write, went to the leader, no problem. But when you reloaded the page, your read request got sent to a follower who was lagging behind. It hadn't gotten the news yet. So you're literally reading stale data, your own stale data. It's a super jarring experience, and it's all because of that replication lag. All right, so if a single leader can be a bottleneck, and if it's a single point of failure for all our writes, the next logical step seems pretty obvious, doesn't it? Let's just add more leaders. Problem solved. Except, well, not really. As it turns out, more leaders can mean more problems. Now, this kind of setup is awesome for big global apps. You can see here we can stick a leader in a European data center and another one in an American data center. So now users in Europe write to their local leader and users in the US write to theirs. Performance is amazing. It's super fast. But all this goodness comes with a brand new, really thorny problem. And that problem is write conflicts. So here's the big question. What happens if two people on opposite sides of the world try to edit the same exact thing at the same exact time? With just one leader, it's easy. One person's change just gets in line behind the other. But with two leaders, there's no single referee to decide whose change came first. And this is what you get, a write conflict. Look at the diagram. User 1 tells leader 1 to change the title to B. At the same time, user 2 tells leader 2 to change the same title to C. From their perspective, both changes worked. It's not until later, when the leaders try to sync up with each other, that the system throws its hands up and says, whoa, wait a minute. So the big takeaway here is that you've gained speed and reliability, but you've paid for it with this really nasty problem of conflict resolution. And if you don't handle that perfectly, data just gets lost. Okay, so that brings us to our third and final approach, which is maybe the most radical of all, leaderless replication. This idea was really made famous by Amazon's Dynamo system, and it does exactly what it says on the tin. It completely gets rid of the whole idea of a leader. Any copy of the data can take a write from a user. The way this works is kind of like a democracy. It uses something called a quorum. To save some data, you have to send it to several replicas and get confirmation from, let's say, W of them. That's your write quorum. To read the data, you have to ask R replicas. That's your read quorum. And here's the really cool part, the magic formula. As long as W plus R is bigger than the total number of replicas, N, then you are absolutely guaranteed to read the latest version of the data. This visual really helps it click. So imagine we have 5 total copies, so N is 5. We decide that for a write to count, it has to be confirmed by 3 of them, so W is 3. And for a read, we'll ask 3 of them, so R is 3. Now just do the math. 3 plus 3 is 6. And since 6 is more than our total of 5, it is mathematically impossible for the group of nodes you read from not to overlap with the group of nodes that received the latest write. There has to be at least one in common. It's a guarantee baked right into the numbers. So we've looked at these 3 totally different ways of doing things: single leader, multi-leader, and leaderless. It brings up the big question, right? Which one is the best? Which one should you actually use? And the honest answer is, there is no best one. It's all about trade-offs. It always is. The single leader model is beautifully simple, no conflicts to worry about. But you have this single point of failure, and you need a solid plan, a failover process for when it goes down. The multi-leader approach gives you fantastic availability, but you're signing up to solve those nasty write conflicts. And the leaderless model? It's the king of fault tolerance, but figuring out its consistency guarantees can honestly make your head spin. And that really leaves us with this one last thought to chew on. Every single app you use has one of these designs running deep in its core, and that design directly shapes your experience. It forces the people who build these apps to make a really tough call between showing you the absolute latest data instantly and making sure the app is always there when you need it. And in a way, that choice says a lot about what they believe is most important to you.